Hello, my name is Foster Van Fleet. I am a computer science major at Millersville University. Today, I am going to go over a project I did involving machine learning or data science in sports betting. For a quick outline of how this presentation is going to go, I will quickly do an introduction so that you better understand the concepts that are important or understand the industry of gaming and sports betting. I will then do a data and pre-processing, talking about my raw data and how I transformed it into what I end up using, the methods or the models that I used, my results and discussions, and then a conclusion. So we'll start with a quick introduction. As you can see on the right side of this slide, we have a sports betting ticket. I thought it would be good to just help you visualize kind of the data that they would get from a ticket. You have a ticket number, the bet type, the number of bets, the bet number, the bet amount, the bet payout, and the entire amount you take home. The only other thing that I think is on this ticket that they didn't label, which would be great to understand, is the minus 110 right above the ticket cost. That is the odds, and we do have that, and it was an essential part of my data, so I think it was important to point out. I think another thing that we should really discuss is kind of the dynamic nature of sports betting. So, in sports betting, these lines or odds are changed in real time based on unexpected variables, such as injuries, weather, and much more. With that said, it's really inefficient and difficult to get that data and then transform the odds based on that data. Because of this, there is a space or gap for opportunities for people to gain an edge or real positive expected value over the book and on a bet to bet basis. Sportsbooks need to identify which customers are valuable and which pose risk. And that is what the goal of my model will be to do, is to predict the value of players based on how they bet, what they bet, and so on. Some terms I think you might want to know to better understand the mathematics and concepts that are essential to the sports gaming or the gaming industry. One of them, and most importantly, I think, is expected value. This is the amount a bet is on average expected to win. For an example, and the same example I will use for all of these, is a coin flip. For the probability, we're expecting it to be heads or guessing that it's going to be heads. That is 1 over 2, because it could be heads or tails, multiplied by the observation, which in the scenario would be the wager. So if my wager was $10, my expected value would be $5. The actual value, this is the amount that the bet actually won. So in that same scenario where we have a coin flip and we guess heads and we wager $10 and we won, the actual value is going to be $10. Whereas if we lost, the actual value is going to be $0. This leads right into variance. Just understand that expected value is not always equal to actual value. The amount of time or quantity of bets for actual value to near the expected value is called N0. And this is kind of a really important concept, which we will talk more about later. But you just need to understand that it takes a long time for variance to work itself out and for actual value to near the expected value. So this slide has my raw data. The table on the right that you see is directly from my CSV. The only thing that I did cut off was my leftmost, and that was just to make it fit the slide, but the leftmost was the rows, which was each row was a unique bet ID. This data set contained 100,000 rows with 5,000 unique user IDs and approximately 20 bets per user. It included data types such as numerical, categorical, and Boolean. I will go through each one of these columns really quickly. User ID is a unique ID for the user. I would eventually aggregate these columns by this user ID. The bet type is actually, bet type and sport were both not used. However, I do think it would be interesting to include them to see if there is behavioral patterns that are risky or valuable to the book. odds, which this odds is a little bit of a different format than what the ticket was, but I believe this is a little bit more readable for most. Is win is just a true or a false for that bet, did it win? Stake is how much the user wagered. Gain is how much the user won. If they didn't win, then it is 0. And GGR stands for gross gaming revenue. This is how much the book makes or loses from a bet. This is going to be what we are eventually trying to predict on a per user level, is how much GGR they average, either win or have given per bet to the book. Preprocessing, we kind of just went over a little bit of what I had done, but I aggregated by user ID, and that created the columns of number of wins, total stake, total odds, total bets, total gain, total GGR, and it also I counted the number of bets per each user. I then used that table to create what I called user behavior data. This included columns such as average stake, average odds, win rate, average GGR, stake times odds, stake standard, high odds win rate, and low odds win rate. All of the user behavior data were features that I did end up using in the model. Here is a table that just shows how I got each of those features. For example, I got average stake from total stake divided by number of bets, and so on. I don't think we need to spend too much time on this. However, I would like to mention that stake standard and odds standard, these are just the formulas for standard deviation, and I label what the x is and what the mu is, and the n is obviously the sample size. High odds win rate and low odds win rate, these were arbitrarily picked 3. I guess I could have probably done some sort of math to find what the median odds is, but I just chose 3 as I figured that was a good number. Behavior volatility is stake standard times odd standard. So we are going to talk about some collinearity that is possibly and likely occurring, and that's because stake standard and odd standard make behavior volatility, but all 3 of those were used in the model. So for my very first model that I built, I used a linear regression model to predict the average GGR of a user. My first model was trained on the features number of bets, average stake, average odds, win rate, and stake times odds. The performance of this model had a root mean squared error of approximately 84. When I first saw the root mean squared error of 84, I was concerned that was performing pretty poorly. An average GGR was the standard deviation of an average GGR was 94.921, and I kind of picked that to be my baseline. It is a little bit of an arbitrary baseline, but what it does show is that the model is predicting directionally correct, however, not very precisely. That leads me to my second model. Still using the linear regression model, but I added some new features. I added stake standard and odd standard. These features were added with the intention to limit the impacts of users who have large swings in their betting behaviors. At least that was my hypothesis for why I should be using those features. The performance of this one was a root mean squared error of 83, which, if you recall from the last slide, my root mean squared error of the first model was 84. So there wasn't really any significant difference or change in how my model performed. Due to my lack of improvement in performance, I decided I needed to do more. So I decided to use a ridge model, and I used some new features. I used the same features as the second model, but I also added high odds win rate, low odds win rate, and behavior volatility. These features were added with the intention to better capture the user strategies and their success rate. I want to mention that I didn't do this in one iteration. I actually implemented the high odds win rate, the low odds win rate, and the behavior volatility before I implemented the ridge model. And the ridge model is what drastically reduced my root mean squared error, not the new features. The new features did help, but not as much as the ridge model. And as you can see, the performance of this model was a 76.56 for its root mean squared error. That is a sizable improvement in performance from the previous models. So for a results and discussion, I think this is probably the most important slide of this presentation. The performance of my model had a large enough error rate that I think it would be unwise for companies to use its current state to specifically or confidently identify which players are winning players and which players are losing players. However, I think there is a reason for this error rate, and that said, I don't think it's necessarily about the model and just about the amount of data. To explain that, let's put the data into context. In sports betting, N0 is very large, and if you remember from one of the earlier slides, N0 is how long it takes for the variance to kind of weigh itself out. And it's due to a small odds and large variance that this N0 is very large. The N0 will also be different for each bet because of different odds per bet, and that makes it really hard to quantify what the N0 would be for a single user. However, I did try to do some math and try to figure it out, and my best guess, it was approximately 500 bets per user. And again, it is hard to quantify because some users are going to have higher odds and therefore they are going to have much higher N0s. So what that means is that this data is inheriting a lot of noise from the variance. To improve this model, I think I would need a lot more data, or specifically bets per user, and I believe I would need at least 1,000 bets per user. That is far more than the approximately 20 bets I had per user. However, I also think that this model is not a failure. I believe that this created a lot of important interpretations of what makes a user valuable and risky. And it is also good to know that the model correctly predicted 5 out of the top 10 highest GGRs. For a baseline comparison, if we randomly picked a person and we're hoping to get them in the top 10, it would be a 1 out of 20 chance. So it is performing significantly better than just guessing. As I had mentioned, there is more value to a model than just how accurate it was. For example, I'm going to try and use the coefficients to make informed hypotheses and conclusions to gain a better understanding of what characteristics actually matter to the value of a user. To go through these values, I think it's important that we ignore the magnitude or at least put it into context, as different features are going to have a different range of values. For example, my win rates, they are all going to be in between the range of 0 and 1, or a decimal. And therefore, those win rates are going to be much larger numbers, or ignoring sign, at least much larger numbers. For example, we have low odds win rate is 52, the win rate is 341, and the high odds win rate is 229. And then if we compare that to numbers like stake and odds, those are always going to be larger than 1, or at least almost always going to be larger than 1, and their range is 0 to infinity. So it makes sense that the numbers or the coefficient values associated with these features are much closer to 0. My most interesting results were odds standard and stake standard. These were positive and impactful to GGR. Players who have large swings in betting behavior are potentially valuable to the book. I think this makes sense upon further inspection, as a player who has a lack of betting discipline or is behaving erratically based on previous wins or losses would be good for the book. And then to further that, I think it would be interesting if we took this and put it in a time series model to see if people's odds standard or users' odds standard or stake standard changed drastically based on previous wins and previous losses. Behavior volatility is negative. If you recall, odd standard and stake standard multiplied together is how I got behavior volatility. I just mentioned that odd standard and stake standard were both positive and impactful, but behavior volatility is negative. I believe this to be an effect of the ridge model, spreading the collinearity of the three features amongst each other, and that made behavior volatility slightly negative. I would probably remove this feature if I ran another iteration of the model. Another feature that I would remove is the low odds win rate, and that's because this poses a little bit of a paradox. So, a player who has a large low odds win rate, or they are successfully winning at the low odds amount, these are going to be a risk to the book. Not a large risk because the book isn't paying out much when they do win, but these are still going to be a risk. And players who have a small low odds win rate or are unsuccessful at winning at the low odds amount, they are going to be valuable to the book. But as you can see with this coefficient value, it is not so. We are having the opposite happen. So therefore, I believe removing it may actually be beneficial. In conclusion, to summarize what we have talked about, with the current data set that I have, I cannot precisely or at least confidently detect the value of users. I would like to investigate if there is a correlation between the previous wins and losses on betting behaviors. We can identify characteristics and behaviors associated with user risk and value. And this industry has very noisy data, and the sensitive nature of the data makes the data hard to obtain. Thank you very much for listening to my presentation. I greatly appreciate it. I mean, you took the time out of your day to do this. Don't gamble. Gambling is a very addictive and dangerous habit. So yeah, don't gamble, and thank you for listening. You have a great day.